Solutions. Solutions are very important in chemistry. They not only provide a medium in which many chemical reactions occur, but they also exhibit certain special properties that pure solvents do not. And in this lecture, and also the next couple of lectures, we'll study solutions in pretty good detail. Not only defining what solutions are and what's involved as a solution forms, as well as what are the solution concentration units that we use, but also what are these special properties that solutions exhibit and why do they exhibit them. But before we get into that level of detail, let's first recall some basic information that you might recall from first semester general chemistry. A solution is defined as a homogeneous mixture of two or more substances in one phase. A mixture is a solution when the components of the mixture are mixed together in a homogeneous fashion. That means all of the components have been completely broken apart into their smallest pieces and have been thoroughly mixed together. You cannot have a large clump of one component that has not been broken apart yet. All of the components need to be completely broken apart and mixed. Now I've listed several examples of solutions here. One of the most popular solutions is salt water. Here water is the solvent, and salt, or table salt, which is sodium chloride, is said to be the solute. Now the solvent is the component that's present in the most abundance, and the solute is less abundant. And it's described as the solute is dissolved in the solvent. So this is a liquid phase solution. Another liquid phase solution is sugar water. And again, water is the solvent, and table sugar or sucrose is the solute. Now in our course, we will actually focus on liquid phase solutions and more specifically aqueous solutions. However, it's good to be aware that gaseous solutions and solid phase solutions also exist, and I've listed a couple of examples here. An example of a gaseous solution is air. Now, air is mostly nitrogen. In fact, about 80% of air by mass is nitrogen, so it's considered as the solvent. The rest of the 20% of air is mostly oxygen, but perhaps a fraction of a percentage is carbon dioxide and maybe a couple of other trace components as well. So it's definitely possible to have more than one solute dissolved in the solvent, like in air. A few solid phase solutions are listed here. A popular one is brass, which is mostly copper with some zinc dissolved in the copper. So zinc is considered as the solute since it's a little less abundant. Now a few unorthodox solutions that are solid phase are crystals. It's really interesting how a crystal can be considered as a solution. And amethyst is actually silicon dioxide, which is really quartz crystal. And if you recall from our previous lecture, quartz crystal is a nice clear looking crystal. And you can imagine the crystal lattice of quartz, if you distribute throughout that lattice a few iron 3 pluses here and there in a homogeneous fashion, the iron 3 pluses affect the electronic properties of the crystal in such a way to give amethyst that nice purple color. So again, really interesting how a crystal can be considered as a solution. You have your pure solvent, which is the quartz, and the iron 3 pluses that are distributed here and there throughout the crystal lattice is the solute. Another crystal solution is ruby. Ruby is aluminum oxide, which is a clear corundum crystal. And again, if you imagine that crystal lattice of the aluminum oxide, nice clear crystal lattice, however, if you distribute a few chromium 3 plus ions here and there in a homogeneous fashion, they again affect the electronic properties of the crystal in such a way to give ruby that nice red color. Now, here are a few examples of mixtures that are not solutions. The first one is marinara. If you make marinara like I do, you will have large clumps of tomato, onion, garlic, and perhaps some other components as well. So again, these components have not been thoroughly broken down into their smallest pieces. So this is not a homogeneous mixture and definitely not a solution. You describe it as a heterogeneous mixture. Another heterogeneous mixture that's not a solution is cement. Cement has large chunks of rock and perhaps other debris mixed throughout the cement. So again, heterogeneous, not homogeneous. Now the last example might come as a little surprise. Mud water, which is dirt mixed with water. Even if you mix that dirt up really well and you get that nice cloudy mixture, it's still not a solution, because after all, you can grab a magnifying glass and look at the mud water and see those little dirt particles that are floating around. And if you can see them with your eye, that means the dirt particles on the molecular level are huge, and millions of dirt particles make up one of those little specks that you see. So again, it has not been completely broken down into its smallest pieces. And you can even filter out the dirt using a filter paper, collect the water underneath, and trap the dirt on top of the filter paper. So, not a solution. Now in this course, we will focus on liquid phase solutions, and more specifically, solutions where water is the solvent. These are called aqueous solutions. And I've drawn a couple of aqueous solutions here so we can wrap our mind around what a solution might look like on the molecular level. The first one is sucrose dissolved in water. This is table sugar. Now when sucrose dissolves in water, and the little AQ in parentheses means it's dissolved in water, the molecules of the sucrose become completely separated from one another. And I've drawn a molecule right here, and you can see that it's separated from that one right there, and they're all separated from each other and mixed together in a pretty even fashion, so a homogeneous solution. Another example of an aqueous solution is sodium chloride dissolved in water. However, when sodium chloride dissolves in water, something different happens in that the cations become separated from the anions. Now the reason that happens is because water is a polar molecule. And if you recall from our previous lecture, water molecules have a dipole, meaning it has a negative end and a positive end. The oxygen of a water molecule is electronegative, and it pulls electrons towards one end of the molecule, leaving the other end partially positive. And this dipole on the water molecule is very good at pulling apart cations from anions when ionic compounds dissolve in water. And so what you end up with are a bunch of cations floating around separately from the anions with water surrounding them in a homogeneous fashion. Now, because there are charges in this mixture right here, it has a special property in that it conducts electricity. And you can see that by taking two terminals of a battery and immersing them in the water, and you'll see that electricity is able to flow from one terminal to the other. And the reason that happens is because the charges help the electricity flow. Now we'll talk about electricity flowing through water and electrochemistry in a later lecture, but it's really interesting how some solutions are able to conduct electricity because they contain ions and others do not. You call them electrolytes and non-electrolytes. Now with solutions, you can ask many questions, and perhaps one of the first questions that you ask is, how much solute is dissolved in the solvent? And there are several answers to this question, and you can take a naive approach and say that there is just a little bit of solute dissolved and call the solution dilute. Or you can say that there is a lot of it dissolved and call the solution concentrated. One or the other. you can probably guess that's not going to be good enough for this course. We need a more quantitative measure of solution concentration. There are many different measures of solution concentration, and in this course we'll be needing 3 of them. The first one you probably recall from first semester general chemistry, and that's the molarity. The molarity is defined as moles of solute divided by liters of solution. So the units here are moles per liter, or simply capital M for molarity. Now we should note that this is a temperature-dependent measure of concentration, and that's because the volume of solution, which goes down here in the denominator, can vary depending on the temperature. You should recall that solids, liquids, and gases all expand a little bit when you increase the temperature. Gases more so than solids and liquids. However, they still expand a little bit, and under hotter temperatures, the volume of solution would be a little bit bigger, which would make the molarity a little bit smaller. Now, this example shows how to calculate the molarity. Find the molarity if 5.22 grams sodium chloride is dissolved in enough water to form 125 milliliters solution. So to do this, we need moles of solute and liters of solution. The calculation is done using dimensional analysis, so let's see how this goes. Starting with the mass of the solute, 5.22 grams of sodium chloride, we convert that to moles using the following conversion factor, 1 mole over 58.44 grams. And if you do the calculation up to here, you have moles of sodium chloride. So we need to divide by the liters of solution. So the first thing we do is multiply by 1 over 125 milliliters. That's the same thing as dividing by the milliliters of solution. And we can change that unit in the denominator to liters by the last conversion factor, which is 1,000 milliliters over 1 liter. So doing the multiplication, you can check your units, you end up with moles per liter. And you get 0.715 molarity. Now the next measure of concentration is kind of similar. The molality, indicated by a little m. Here the molality is moles of solute divided by kilograms of solvent. Notice here it's solvent this time, not solution. And it's mass of solvent. So this is a temperature independent measure, and that's because the moles and the mass do not change with temperature. So under hot conditions or cold conditions, the molality would always be the same. The example shows how to calculate the molality. Find the molality if 10.5 grams potassium bromide is mixed with 212 grams water. So again, using dimensional analysis, starting with the mass of the solute, 10.5 grams potassium bromide, converting to moles using the molar mass, and then dividing by the mass of the solvent, which is 0.212 kilograms. So working it out, you get moles per kilogram, or molality, and you get 0.416 molality. Now the last measure is probably the simplest, and that's the mole fraction, which is represented by this Greek letter chi. The mole fraction is defined as moles of solute over total moles in solution. So to determine the mole fraction, you need to know the moles of everything in the solution. The following example shows how to do this. Find the mole fraction of potassium bromide if 7.31 grams is mixed with 50 grams water. So we do need the moles of everything in the solution, and that's potassium bromide and water. So to find the moles of potassium bromide, we start with its mass and we convert it to moles using the molar mass again. and you get 0.06143 moles potassium bromide. This is a 3 sig fig number. I left the extra digit because we're going to use this number again. The moles of water is calculated the same way, mass over the molar mass, and you get 2.775 moles water, again a 3 sig fig number. So a lot more moles of water here than potassium bromide. So we should expect the mole fraction of potassium bromide to be kind of small because there's not very many moles of it. So the mole fraction is defined as the part over the whole, just like any other fraction. And we take the part, which is potassium bromide, 0.06143, divided by the whole, which is all of the moles, 0.06143 plus 2.775, and you end up with 0.0217. So that's a pretty small fraction, which is potassium bromide. Now, if you wanted to find the mole fraction, which is water, it would be done the same way, except in the numerator, it would be moles of water. But you don't really need to do that because, after all of the fractions add up to 1, and if you find one of the fractions, then the other one is just whatever you add to this to get 1. And so the mole fraction of water would be 1 minus the mole fraction of potassium bromide, and that's 0.9783. So there are other concentration measures that are out there. We just won't be using them, but they're worth mentioning. One is the mass fraction, which is very similar to the mole fraction, except it would be the mass of the component over the total mass. And a very closely related unit, which is mass percent, and that's simply the mass fraction multiplied by 100. There are other concentration units you might see from time to time in other areas, and that's the parts per million and parts per billion. The parts per million is kind of like the mass percent, except it's the mass fraction times a million. And the parts per billion is the mass fraction times a billion. These two are used to measure very small dilute solutions. A useful skill to have is to be able to convert from one type of concentration unit to another. However, such a conversion is not as trivial as some of the unit conversions that we're normally used to doing are. And that's because concentration units are inherently different from each other, and doing those calculations requires a little bit more care, and as we'll see, a trick or two. First, let's recall a normal type of unit conversion, and you may have seen this one before. Let's take 55 miles per hour and convert it to meters per second. Now here the starting unit and ending unit are both units of velocity, and they're of the same type. Although this is a derived unit, it has a unit in the numerator and a unit in the denominator. We know the relation between this numerator unit and that numerator unit. We can go from miles to meters pretty easily, and we can go from hours to seconds fairly easily also. And so we just do it one at a time here. To take miles and convert it to meters, we first convert miles to feet, then feet to inches, inches to centimeters, centimeters to meters. So the numerator unit has been adjusted. To go from hours to seconds in the denominator, we throw in the last conversion factor, where 1 hour is 3,600 seconds. And so all of the units have been changed, and we end up with 24.6 meters per second. However, converting one type of concentration unit into another is a little bit different, and that's because the units are not of the same type. For instance, to go from molarity to molality, molarity is moles solute per liter solution, and molality is moles solute per kilogram of solvent. So whereas the numerator units are the same, the denominator units are of a different type. We need to take liters of solution and convert it to kilograms of solvent. That's a little bit tricky. So what we're going to do is to take 3 molarity of HCl solution. We're going to convert that to molality, then convert molality to mole fraction, and then finally mole fraction back to molarity again. So we should end up with 3 molarity. Now to do the first conversion, we'll be needing the density. And the density of 3 molar HCl is 1.05 grams per milliliter. So the trick here is to assume a convenient amount of solution. Concentration is an intensive unit, and it doesn't matter how much solution you have. So let's just assume a convenient amount, and that is 1 liter of solution. Because we're starting with molarity, if we assume 1 liter of solution, that means we have 3 moles of HCl. So we know exactly how much HCl we have. But we need to convert 1 liter of solution and figure out how many kilograms of solvent there are. So here's how we do it. We take our 1 liter of solution, convert it to milliliters using that relation, then convert the milliliters to grams using the density, and we end up with 1,050 grams of solution. Now if we can subtract off the mass of the solute, we would then have the mass of the solvent. Now we can do that because we know in 1 liter of solution we have 3 moles of HCl. So we can take our 3 moles of HCl, convert it to grams using the molar mass, and that means we have 109.38 grams. So we take our mass of solution, subtract the mass of the solute to get the mass of the solvent. So now we have all the pieces that we need. We know that we have 3 moles of solute, and we take that and multiply it by 1 over 940.62 grams of solvent. So now we have moles of solute per grams of solvent. We need moles per kilogram. So we throw in the last conversion factor, and now we have moles of solute per kilogram of solvent, and that's the molality. And we end up with 3.189 molality. Molality is usually pretty close to molarity as long as the concentrations are fairly dilute and the density is roughly the same as that of water. So let's take our 3.189 molality and convert it to mole fraction. Now here we need to pick another convenient amount of solution, and the convenient amount this time is enough solution that contains 1 kilogram of solvent. Now this is a convenient amount because we know what we're starting with. If we start with molality and we assume 1 kilogram of solvent, then that means we have 3.189 moles of HCl. So to get to mole fraction, we need the moles of HCl and the moles of water. So we already have the moles of HCl, so let's get the moles of water. So we take our 1 kilogram of solvent, which is water, we convert it to grams, and then we convert the grams to moles using the molar mass. And you end up with 55.509 moles of water. So we have moles of HCl and moles of water. We can get the mole fraction. The mole fraction of HCl is the moles of HCl over the total number of moles. And you end up with 0.05433 as the mole fraction of HCl. Let's take our mole fraction of HCl and convert it back to molarity. So 0.05433 as the mole fraction of HCl. Now again, we need to pick a convenient amount of solution, and the convenient amount as we did before, is convenient for the starting unit. So a convenient amount for mole fraction is just to assume 1 mole total in the solution. If you have a 1 mole total in solution, that means you have 0.05433 moles of HCl, and the rest of the moles, which is 1 minus this number, is the moles of the water. So we take our moles of HCl and their moles of water, and we convert them to grams of HCl and grams of water using the molar masses. So we end up with 1.981 grams of HCl and 17.036 grams of water. And if we add these two masses, we get the total mass of solution. Now, we can convert our mass of solution to liters of solution using the density again. So we already know how many moles of HCl, and we know how to get to volume of solution, so we should be able to get to molarity. And here's how we do it. We take our 0.05433 moles of HCl, that's a typo right here, that should be 0.0, and we convert that by multiplying by 1 over 19.017 grams of solution, and we change that to milliliters of solution using the density, and then finally milliliters to liters. So if you do this calculation, you end up with moles of HCl per liter of solution, and you get 3.000 molarity. So in this lecture, we have gone through and we have defined what a solution is, as well as a couple of interesting things regarding solutions. We've also talked about solution concentrations. In our next lecture, we'll get into the enthalpy of solution formation. So what happens when a solution forms? And there are some rather interesting things regarding the enthalpy as well as the entropy. And we'll also get into Henry's law. So I hope you join me for that. Aloha.